This is slide number 33 and I am your presenter Asloob Mudassar. Spatial light modulator. Spatial light modulator is actually which is abbreviated as SLMs. This is a device that can be used to generate objects in the transmission mode or objects in the refraction mode, both in coherent and incoherent form. So let's read the description. Input objects which are now obsolete are photography negatives. They are no more used in optical setups because no real-time modifications can be made on the photographic negatives. Optical transparencies generated through the computers. We can also generate objects, for example, especially the objects in the transmission mode using computer printers. That is, we design a pattern on the computer software and then print them on the optical transparencies. Again, the optical transparencies we cannot modify in real time the information on such objects. Now the optical transparencies made with optical means on glass emulsions. So this is another method in which the optical transparencies are generated using optical means. Again, this method is limited in the sense that no real time modifications can be made over here. Now SLMs are very useful. SLMs can serve the purpose of modifying the inputs in real times presented to an optical system. So SLMs are the devices that are used to convert electronic data into spatial format, either coherent or incoherent. SLMs can generate optical objects with controlled amplitude and phase distribution. So you can generate any object either in the transmission mode or in the reflection mode, and you can also have a control, that is the online control. That online you can change the amplitude distribution at the object plane and also the phase distribution. Both can be changed according to your requirement. SLMs are available both in transmission and reflection modes. You can see in the picture that there is a computer connected with the electronic box, and that electronic box is connected with the SLM screen, and which is mounted on an optical stand or optical mount. So the patterns can be designed in the optical computer, and then it is transmitted through electronic box to the SLM. So SLM is in the transmission mode here in this case, which has been shown. You can generate any object, and from the left you can pass the light through it, and you have the phase modifications. That is, you can change the thickness in the SLM. You have the phase modifications and you have the amplitude modifications, and both you can generate the phases in such a way that you can generate an object as a coherent system or as an incoherent system. Now SLMs may take inputs in the form of an electronic signal or in the form of an optical image, and are correspondingly referred to as electrically written SLMs or electrically addressed SLMs, and optically written SLMs or optically addressed SLMs. SLMs exist in different technology. For example, liquid crystal based SLMs, magneto-optic based SLMs, deformable mirror based SLMs, multi-quantum well based SLMs, and acousto-optic based SLMs. The detail of these are beyond the scope of this course. SLMs can also act as complex filters in real time in transmission as well as in reflection mode. The amplitude and phase distribution of the incident light can be changed very precisely in real time. Sampling at the object and image plane. This is a very important topic, and because without the understanding of this topic we cannot do any calculations, because the sampling is very important. The image of a point source on an object plane, that is, a point source is located on an object plane, and we have an optical system through which the image is created, and a single diffraction limited lens is used to create an image. The image is in the form of airy pattern, the central portion of which is shown in the figure. So in the figure you can see that there is a central disc, very bright disc. Around that there is a first ring, and then again there is a bright ring, and successively we have bright and black rings successively unless they diminish. So we can refer to them as the central disk may be referred to as the main lobe, and the other rings may be referred to as the side lobes. So the image of a point source on an object plane by a single diffraction limited lens is an airy pattern. So this is called an airy pattern, the central portion of which is shown. So the lens, so there is an object, so there is a point source which is imaged by the lens, and the airy pattern is generated. So this airy pattern can also be generated if the lens is illuminated with a plane wave which is normally incident on the lens. So let's see, the lens aperture being circular, diameter d, is completely illuminated normally by a unit amplitude plane wave. The image plane calculation is given by. So you see that we can also generate this pattern if you illuminate a lens with a normally incident unit amplitude plane wave, then at the back focal plane of the lens this airy pattern is generated. So since this is generated at the back focal plane of the lens, we can also regard that plane as the Fourier transform plane, because the Fourier transform plane exists at the back focal plane of the lens. So in order to calculate this pattern, we have to take the Fourier transform of the circ function. Circ function mean that the circular function of the lens which is being illuminated. And you know that in the circ function on the left, we are not multiplying with any to the circ function except 1, because 1 the plane wave which is normally incident has an amplitude equal to 1, because we can disregard the phase of such a wave, because the phase is constant on the whole plane. So in the circ function I have multiplied only 1, and I have omitted any constant phase factor. So let me take the Fourier transform of the circ function defined in the Cartesian coordinates as x square plus y square, the square root of x square by y plus y square. And you know that previously we have calculated that the Fourier transform of the circ function is a Jink function. So Jink of fx square plus fy square, the square root of that one. So you see that now this Jink function is related with the Bessel function of a first kind order 1 as j1 of 2 pi square root of fx square plus fy square under the root, and again divided by the square root of fx square plus fy square. So this pi r square should not be present over here. Okay. Now you can see that there are two vertical lines on this airy pattern. One is passing through the lens, through the disc center. The other is passing through the center of the first ring. The two vertical lines are shown on the airy pattern, one through the center of the main lobe and the other through the first minimum. Now consider two point sources at the object plane and the two corresponding airy patterns at the image plane. When the object point sources approach each other, so do the corresponding airy patterns. When the center of the main lobe of the second point source coincides with the first minimum of the first airy pattern, the two object point sources are said to be just resolved, which is the classical Rayleigh resolution limit. So what I mean to say is that this corresponds to, you know that this corresponds to, this is the image of one point source, and the one point source is located at infinity. From that point source, the plane wave front is reaching over lens, and the lens is generating the airy pattern at its back focal plane. So if there are two such point sources which are located at an infinite distance, both are generating plane waves, but there is a small angle between those plane waves reaching to the lens. So two airy patterns are generated, one close to each other. So if the two stars or if the two point sources in the upper space come closer to each other, what will happen? Their images, that is the airy patterns, will also come closer to each other. And when the second airy pattern approach in such a way that it approaches the center of the black ring, then we can say that the two airy patterns are just resolved. In other words, we can say that the distance point sources in the sky are just resolved. So this is the resolution criteria given by the, which we call it as a Rayleigh resolution criteria, in which the center of the maximum of the second Airy pattern coincides with the first minimum of the first pattern. Now let's assume that the diameter small d is the diameter of the Airy disk. So this central disk has a diameter which we have denoted it by small d. Now we want to do some useful calculations. And you look at this equation, 1 over d is equal to capital D over lambda f. This small d is actually the diameter of the disk of the Airy pattern. Capital D is the diameter of the lens, and the lambda f is the scaling factor due to the optical system. So capital D divided by the scaling factor is equal to 1 over d, and from here you can get the value of d, which is equal to lambda f over capital D. And if you also include the area around this whole disk, that is the area, that is the first black ring, then we need to modify this relationship, that is we need to include a factor which is 1.22. So d is equal to 1.22 lambda f over d. So then this d is the diameter including the main lobe and also some portion of the black ring. So you see that this is the diameter at which the other optical, so this is the diameter if you consider from the center of the optical disc to the center of the another Airy pattern which is approaching to the first pattern, then this should be diameter. The other pattern should not come closer to the first to the center of the first disc by this diameter d. So d is equal to 1.22 lambda f over capital D is the limit that the two Airy patterns can come closer to each other, and again the two distant point source in the sky which are generating plane waves reaching to the our lens. So these two cannot come to the closer in such a way that their Airy patterns are separated by this distance small d. Under such a condition we can say that the two object points located at infinite distance from the lens generating plane waves are just resolved. Now this d is also the distance between the centers of the two Airy patterns under the condition of just resolved. If the separation between the two distant point sources is x naught, now we are assuming that the two distant point source or the two distant stars located in the sky, if they are separated by a distance capital X naught located at a distance p from the imaging lens. So the two stars which are distant stars, their distance from our lens is p, then from the imaging lens, then the two plane waves impinge on the lens. That is, the two distant stars will generate two plane waves which will pass through our lens making some angle. Then we can write down the equation between them as x naught over p is equal to d over f. D is f is the distance between the lens and the image plane, and p is the distance between the lens and the object plane. X naught is the separation between the two point sources or between the two stars, and this d is the corresponding distance in the image plane, that is between the center of the two Airy patterns when they are just resolved. So we can find x naught is equal to p into d over f, and if you put the value of d over here, which is equal to from the above, that is from here, d is equal to 1.22 lambda f over capital D. If you put this value of d over here in this expression, you will get x naught is equal to 1.22 lambda p over capital D. So you see that in order to resolve x naught, we have to follow these expressions. So if d is made larger, that is, if you use a lens of a larger diameter d, then you know that you can resolve the objects which are at closer distance x naught. So x naught, the two stars or the two point sources can come closer to each other if you can use a lens of diameter larger diameter d. So the diameter of the lens will control the resolution or will control the separation between the two object points or between the two point sources which can be resolved. So the greater the value of d, the smaller the two point sources or the two point objects come closer to each other such that they can be resolved. according to Rayleigh resolution criteria. The two object point sources should be at least x naught apart if they need to be resolved by a diffraction limited length of a focal length f and diameter capital D. Note that a diffraction limited lens is an isoplanitic lens having no aberrations and its performance is limited only by the diffraction. You know that we have described this isoplanitic region or the isoplanitic region earlier. That is, this is the region where the lens would not show any defects, that is any aberrations, and the only limiting factor that will limit the performance of such a lens will be the diffraction. Now x naught is one limit to the resolution that comes due to the lens. So you see that if you have a lens of fixed diameter, then you know that x naught is also fixed because the lambda, the light coming from the stars is fixed. The p, that is the distance of the stars from your imaging lens, is also fixed. And so if you fixed d, it means that you fix the separation x naught for which the two point sources or the two stars can approach each other and are just resolved. X naught is one limit to resolution that comes due to the lens. The main limit comes from the distribution of sensors in a camera or charged coupled device which is placed at the imaging lens. Next limit to the resolution will be due to the imaging sensor will be worked out. Now you see that here we have mentioned the limit to the resolution at the image plane at the object plane x naught related with the parameters of the lens of the diameter of the lens. But you know that this is the optical limit to the resolution, but there is another limit which we call the geometric resolution, and that will come to the system by the pixels of the array, or by the CCD pixels, by the pixels of the charged coupled device, or if you put your mobile cameras over there, then the separation between the pixels of the camera, that will limit the resolution of the system. Let's work out that limit. So limit to resolution due to imaging sensor. So you see that your mobile camera has a large number of array of sensors. The sensors are placed in a regular shape, or in the charged coupled device we have a charged coupled device is actually it has the sensor which works in the same way as the sensor of your mobile camera, but you know that the CCD is more precise, more accurate, and more accurate arrangement of sensors and more accurate quality of the sensors in the CCDs. Now consider an array of pixels as array of point sensors. So we are considering the array of pixels as the array of point sources. That is, we are considering that the pixels are very small, so that we can consider them as point sensors with the separation capital X between them along the horizontal direction and separation capital Y between them along the vertical direction. Then the image sampled by such an array of sensors, and the sampled image is referred to as the O subscript to S at the point xy with a signal which is falling on such an array. This signal O at the point xy is a continuous signal, whereas the OS is a sampled signal. The continuous signal will fall on the array and the sampled signal will be generated. So you see that we have shown the array over here. Look at this array. Along the vertical side, the separation between the pixels between the point sensors is capital Y. Along the horizontal axis we have the separation which is capital X, and we have shown the X and Y direction on this array. We have shown a small portion of that array, but this may contains millions or millions of pixels, or maybe for example today's mobile cameras have 50 millions of pixels, and even 100 millions of pixels are also available today. Now you see that if an object which is continuous will fall on this sensor array, the sensor array will give you an image which is we call as OS. That is the sampled signal. So OS which at the location of XY will be equal to the comb of X over capital X into comb of Y over capital I and on which the signal O is which is the continuous signal O is incident on this one, and this comb way, as you have the comb used to comb your hair, you see that this is the same comb function in mathematics, that is just acting as an actual comb you use for your for combing of your head hairs. So comb of x over x means that you have the sensors which are separated by a distance capital X, and comb y over y is that you have the pixels along the y direction which are separated by capital Y. So you see that here in the figure below I have written that an array of sensors in a CCD with horizontal pitch equal to capital X and the vertical pitch is equal to capital Y. So you have given the pitch of this sensor along the horizontal as capital X, and the pitch along the vertical side as capital Y. And you see that this combo function will help us. Now the combo function is defined below. Comb x over capital X is equal to summation from summation over n, which goes from minus infinity to plus infinity, and delta of x over capital X minus n. So when x over capital X takes that integer values, then you know that this delta function will be 0 over there. It means that the signal will exist or the center. This will give you the position of the point sensors at that locations. For integer values of n, you will get the array or you will get the position of the point sensors, which we have indicated in these two figures. So in the left figure you can see that I have shown the small arrows at the position of each sensor, but on the right hand side I have shown the same figure as on the left hand side, but only the arrows are shown at the position of the point sources. So actually these are actually the delta functions which peaks up at these points. So the combo function is actually these delta functions which peak up at the position of the sensors. So along the sensors, if the delta function is along the x direction, we have capital X is the separation between the sensors along the x direction, and if you are using a comb of y over capital Y, then the separation along the y direction will be equal to capital Y. So here you see that this is the array of sensors or the delta functions or the combo functions over which your signal will fall, and this signal will be sampled. The small o signal which we have represented as a small o will fall on these sensors, that is on the delta functions, and the delta functions will sample them at the points of these arrows where these sensors exist, and will give you the sampled signal which we have given over here. So this is the sampled signal generated by the two combo functions. The two combo functions are actually the combo functions at the positions of the sensors along the x direction, along the y direction with the pitch equal to capital X, along the x direction with the pitch equal to capital Y along the y direction. Now you see that we have to do some calculations in the Fourier domain. That is, we have to calculate the Fourier transform of this equation. So in the Fourier transform, we have the Fourier spectrum of OS, which is a small OS. The Fourier spectrum of this one will be represented by capital OS, and this quantity, which is the continuous signal O at xy, the small o which is in the space domain, so its Fourier spectrum will be capital O at the position of Fourier variables fx, fy, because the Fourier variables are fx and fy. So let's now talk about the before we calculate the Fourier of this whole quantity, let's calculate the Fourier of the combo function, and then we shall plug in their values in that equation. Only the sampled version OS x comma y is available, and to determine the continuous signal O at xy, a very important sampling theorem known as the Whittaker-Shannon sampling theorem is presented. So let's take the Fourier transform of the equation above. Fourier transform of the sampled signal is equal to the Fourier transform of the signal on the right hand side, which contains two combo functions multiplying to the continuous signal O. And if you apply the Fourier theorem, you know that convolution theorem means that the Fourier transform of the first signal convolved with the Fourier transform of the second signal, because the first line the comp function are multiplying with O, and when you take the Fourier transform of that one, then the Fourier transform of the first signal will be convolved with the Fourier transform of the second signal. This is the convolution theorem. Now we have to calculate, in order to evaluate this equation, we have to calculate the Fourier transform of the combo function. So first of all, we are going to calculate the Fourier transform of the first combo function, which we plug in over here. So now the Fourier transform of the first function is Fourier transform of comb of x over capital X is equal to you know that this is the Fourier integral that we have used. You can identify this is the Fourier integral. We have e to the power minus iota 2 pi fx into x, and the integration is with respect to dx. So this is the Fourier integral in one dimension, and there we have put in our function which is comb of x over capital X. Now we in the second row we have put the value of a comb x in terms of the summation signals we have described earlier, that the summation from n is equal to minus infinity to plus infinity delta of x over capital X minus n. Now you see that if you take this capital X common that is out from the delta function, that will be inverted, that is the reciprocal of this will be multiplied with the delta function. So anything that is common from the delta function, that you have to take the reciprocal of that one. So 1 over x, if you take 1 over x common from delta, that will be the reciprocal of 1 over x, which is capital X. So in the third step we have written capital X and the summation sign, and then the integral. We have sent the integral. We have sent the summation on the left hand side of the integral, and there we have the integration, that is delta of x minus n into capital X, because we have taken 1 over x common from the delta function, and then we have written this one. And you know that this is the integral that we can evaluate. If you in the delta function, if you set small x is equal to n into capital X, then you know that in the exponential form you have to replace this capital small x with the n into capital X in the fourth step, and the integration will be solved. So now in the fourth step you have capital X, you have the summation sign from n is equal to minus infinity to plus infinity, and then you have only the exponential sign survived from the integration, but you know that here the small x in the exponential has been replaced by n into capital X. So this is the solution of the comp function. Now we want to use a well established mathematical identity, that the summation, because we have single summation and we have single exponential factor like this one. If you apply this, the summation, the identity of this one is equal to the identity given on the right hand side, that is the left hand side expression is equal to the right hand side summation over n and multiplied by delta of fx into capital X minus n. So this is the identity that we have used. Compare this fx into capital X is present in the argument of the exponent function on the left hand side, and n is also present, but you know that here we have to set that delta of fx capital X minus n is actually mathematical identity. And this identity, if you use the comp function definition we have given above, if you want to write down this expression in terms of the comp function, we have given the above definitions there, comp relating to the expression of this summation sign, then you can write down that this is equal to comp of fx into capital X. So what we have done is that we can now write the Fourier transform of this combo function after solving this identity. The overall relationship is that the Fourier transform the Fourier transform of the comb of x over capital X is equal to capital X multiplied by the comb of fx into capital X. So here you can easily generalize the Fourier transform of the comb function. Similarly, we can generalize the Fourier transform of the second comb function, and we can put the two values over there. So we have the two comp functions. Again, we have capital X capital Y on the left hand side, as we have on this in this Fourier transform of the comp function. Now we are putting the two comp functions together. One contains capital X into comb of fx into capital X. The other Y will also contain similarly what it will contain. So the other will contain, you know, that two comb functions. Fourier transform of comb1 and comb2 is equal to x into capital Y comb of fx into capital X multiplied by comb of fy into y. Now you can put their summation signs that we have evaluated earlier, and then you can combine two delta functions together, because these two are one-dimensional delta functions. You can combine them in the form of two-dimensional functions, but before that you can use their identity. You can take capital X common from these and capital Y common from these two, and these will cancel the capital X and capital Y on the left hand side of these expressions, because when you take a capital X from common from the delta function, it will you have to take the reciprocal of that x, that is 1 over x will be multiplied on the left hand side, and similarly capital Y taken from the delta function, that will be converted to the its reciprocal, which is 1 over y, and so capital X and capital Y on the left hand side will be cancelled out, and you have these two delta functions. Now these two are one-dimensional delta functions. You can combine them into two-dimensional delta functions as given in the last value, that is delta, that is two summation sign. One is over n and the other is on m, and you have delta of fx minus n over capital X comma fy minus m over y. So this is the two-dimensional delta functions. And now we are putting the value of this the Fourier transform of this comb function into our previous equation. Which equation is that? And this is this equation. You know that here we are going to put the value of the Fourier transform of the two comb functions, and then we shall evaluate it. So let's do the further calculations. Okay, now we have the Fourier transform of the sampled signal, which is capital O subscript to S, evaluated at the coordinates fx comma fy, is equal to two summations. One is on n, the other is on m, both from minus infinity to plus infinity, the two-dimensional delta functions, and convolved with the Fourier transform of the continuous signal, which is the original signal capital O evaluated at the coordinate fx comma fy. So when you convolve these two signals, the delta function, the argument of the delta function will replace the argument of the function, that is fx will be replaced, the fx in the signal will be replaced by the argument of the delta function, which is fx minus n over x, and fy in the signal will be replaced by the argument of the delta function, which is fy minus m over y. So lastly we have two summations on the signal capital O, and the capital O, you know, that is now sampled at fx minus n over capital X comma fy minus m over y. So the Fourier transform of the sampled signal. Now on the left hand side you have the Fourier transform of the sampled signal at fx comma fy is equal to the sum of an infinite number of copies of the Fourier transform of the unsampled signal capital O of fx comma fy. So from this mathematical expression you can see that this O, which is the original Fourier transform evaluated at fx minus n over x comma fy minus m over y, these provide you the infinite number of copies going from minus n is equal to minus infinity and m is equal to minus infinity to both plus infinities. So many large infinite number of copies are present of the original signal. This is what we have stated over here. The center of each of which are separated from the neighboring copy by 1 over capital X along the fx direction and 1 over capital Y along the y direction. So these copies which are infinite in number, and these copies are separated by, that is for example, if you put n is equal to 0, the first copy will exist at fx is equal to 0 and fy is equal to 0 if you put m is equal to 0. So n is equal to 0, m is equal to 0 will give you the central copy at coordinates fx is equal to 0, fy is equal to 0. But if you put, for example, n is equal to 1 and m is equal to 1, then you will get a copy on the first diagonal which will be centered at O, centered at fx is equal to 1 over x and fy is equal to 1 over y. But if you want to take the copy on the fx axis, then you need to put m is equal to 0. So if you put m is equal to 0 and if you put n is equal to 1, then the first copy along the fx direction that is the first copy on the right hand side of this will be fx is equal to 1 over x and fy is equal to 0. So this is the equation. So putting the values of n and m, you can generate an infinite number of copies, and you know that the center of the 0th order copy is separated by the center of the first copy by 1 over x along the fx direction and by 1 over y along the y direction. This is what we have stated in this text. If the separation between the neighboring copies of O, capital O, centered at fx minus 1 over x and fy minus 1 over m is greater than the size of each copy. So let's assume that the size of each copy is fx multiplied by fy along the fx and fy direction respectively, then a single copy out of the many copies from these can be extracted. So the condition is that. So you see that since we are talking about infinite number of copies, one of such copies in the center, that is for n is equal to 0 and m is equal to 0, is what we have shown in this diagram. You can see that the width of this copy along the fx direction is capital Fx, and the width of this main lobe, this copy of this spectral copy along the y direction is capital Fy. Now you know that next copy will be located on the fx direction and also along the y direction. But if those copies are separated in such a way that their dimensions are greater than the dimensions of fx and fy along the y direction, then you can separate out those copies. So we have given the condition for the separation of these copies that 1 over x, which is the center to center separation of the copies, 1 over x should be at least greater than or equal to the width of the copy, which is fx, and fy, which is the distance from the center to center of the copy along the y direction, which is 1 over y, should be greater than equal to fy. So these are the conditions. We can write them in the reciprocal form as that is capital X is less than equal to 1 over capital X and capital Y is less than equal to capital Y. So one of the copies from O, which is the copies of which are located at fx is equal to n over capital X and fy is equal to m over capital Y. One of such copies is shown in the figure. Remember that these x and y are what? These are actually related with actually the sampling intervals on the object, that is the sensor separation, that is the sample pitch. So you see that this is in the image plane. There we have capital X and capital Y, and now we are comparing that one at the Fourier transform plane with the width of the Fourier copies. And you know that this capital X and 1 over capital X and 1 over capital Y will determine the separation along the fx and along the fy direction. So this is the central copy for which n is equal to 0, m is equal to 0, or equivalently this is the Fourier spectrum of the object O, that is O at fx comma fy. So we are talking about just only the one spectral copy, that is the central copy of the original object, which is shown in the figure. But in principle there are infinite number of copies which we shall show later on. So this is the end of slide number 33.